Welcome to College Algebra for Business. Today we're going to be talking about solving linear inequalities. The same rules of algebra apply to linear inequalities as well as to linear equalities, or as we usually talk about them, linear equations. For instance, this inequality tells us that 3x plus 2 is less than 4. We're going to use the same rules of algebra. We're going to do unto one side as we do unto the other, subtracting 2 from both sides, so that we're left with only 3x on the left, and that 3x is less than 2. And then if we divide both sides by 3, we get x is less than 2/3. Is this true? How would you check an inequality? Well, let's see. On a number line, what is something that's less than 2/3? Let's see, if that's 2/3, something less than that, well, I could choose 1/3. I could choose, I don't know, 1/100th, but boy, 0 is really handy there. So let me choose the value 0 because it is less than 2/3. And let me check my inequality if I put in 0. 3 times 0 is 0. Add 2 to that, and that is less than 4. My check works. But let's look at graphing our answer a little bit more closely. So if I set up a number line so that I've marked 0 and 1 on here, this would represent 2/3. And my answer is not that x can equal 2/3. In fact, it cannot equal 2/3, but it can be infinitely close to 2/3. So it almost reaches 2/3, and we use what looks like a closed parenthesis to indicate that. And it can be anything less than that. So we can write it that way. Here's another inequality that we can solve. Let's first distribute the 10 to both terms inside the parentheses. 5 minus 10x is less than negative 2x plus 21. Now I want to get like terms on the same side of the inequality as each other. I'll do that by subtracting 5 from both sides and adding 2x to both sides. I've decided I want to move my x's to the left-hand side and everything else to the right. 5 minus 5 over here will give me 0, and negative 10x plus 2x will give me a negative 8x, which is less than or equal to negative 2x plus 2x gives me no x's on that side, and 21 minus 5 will give me 16. Okay, now I still need to isolate that x further. I'm going to divide by negative 8, and that's going to do two things. I'm dividing negative 8 by negative 8. That gives me 1, and that's 1 times x on that side. Because I divided by a negative, I'm going to flip the sign. By the way, it also flips if you multiply both sides by a negative. And my answer is x is greater than or equal to negative 2. Let's see what that looks like on a number line. There's my number line. Here's my negative 2, negative 1. There's a 0. I can keep going with this. 1, 2, 3, etc. But my x can be exactly negative 2 or anything greater. A bracket indicates that the variable can be exactly that value. And the way I remember whether to use a bracket or a parenthesis is that if I remove the middle bar of the E, then I'm left with a bracket. So let's look at both of these examples now, because there is another way that you can express these answers. So let's take a look at x less than 2/3 and x greater than or equal to negative 2. We can also express these in what is known as interval notation. Now, in this case, x can be anything all the way out to negative infinity. It can never reach negative infinity, so it can never be exactly negative infinity. Therefore, we do not use a bracket. We use a parenthesis, and we write negative infinity that way. And then we put in a comma, because this is an interval. It goes from negative infinity to 2/3. And our value there cannot reach 2/3. It has to be less than 2/3, so we use another parenthesis. Now for x greater than or equal to -2, the or equal to means that it can be exactly -2, just as we used a bracket up here in our number line for that inequality. And we use a comma, and then x can go on to positive infinity. It can never reach there, but it can head that way. So there are our answers in interval notation. Time for football. Deflategate, specifically. In 2014, it was alleged that during a game, the New England Patriots had intentionally underinflated their footballs, making them easier to throw and catch. And at least one of the balls, depending on who you ask, sometimes more, was 2 pounds per square inch below the required pressure range of 12.5 to 13.5 psi. Footballs inflated in a locker room and then taken out onto the field, where the temperatures were around 20 degrees Fahrenheit, would have experienced a decrease in pressure of about 1.8 psi. So the question we're going to look at is, knowing the forecast for the game, to what pressure should the Patriots equipment managers have inflated the footballs? NFL regulations require the footballs to be between 12.5 and 13.5 psi. So it has to be within that range. And the equipment manager should have known that the footballs would lose 1.8 psi on their way to the field. So to what pressure should they have inflated them to keep them within those boundaries when they were actually on the field in play? Well, let's take a look at this. Just as we do unto one side as we would do unto the other, we want to share the wealth. We want to be fair to everybody. We want to be fair to both sides of that compound inequality, which is what we have here. We have an inequality sign and another inequality sign. That means we have a compound inequality. So to solve this one, we're going to have to add 1.8 to the middle to get that to be 0, and to isolate our p, we're going to have to add 1.8 on the right side and 1.8 on the left side. And so what do we have then? We have 13, 4, and a 14.3. That's over the 13.5 limit, but that would mean when it was out on the field after a very short time, it would be within the correct range of pressures. So there's my pressure there. Let's take a look at the other side of the inequality. If we add 13.5 and 1.8, we're going to get 15.3, which is very consistent. We started out with a difference between 12.5 and 13.5 of 1 pound, and we wound up with a difference between 14.3 and 15.3 of 1 pound. Everything is still just as balanced as it was. The values are just different. We have found the value for P, which is what we were looking for, the pressure to which the footballs should have all been inflated in order for them to be the correct pressure on the field. And that is in PSI, pounds per square inch. We can, of course, express that in interval notation. I'm going to drop the units for my interval notation. Now, the way I've written it here with these less than signs, that means we would use parentheses. and we would have 14.3, comma, 15.3. And this is how it was indicated in one of the articles that I found. However, actually, the footballs could be equal to 12.5 and 13.5. So if we write it that way, you get an exact sign on either side. So 14.3 would have been okay, 15.3 would have been okay, 14.2 would not. And I'll leave the controversy there. You can, because some of you may be Pats fans, and I still want you to learn math anyways. One last point needs to be made here. The pressure needed to be between 14.3 and 15.3. If we draw our number line, and I'm going to go ahead and use the less than or equals to signs, we could draw this as a bracket, because it can be equal to 14.3 under the symbols I have there, and then it would reach up to 15.3 but not exceed it. It would only be between and including those endpoints. So we could graph it that way. This is an AND statement. It has to be between 14.3 and 15.3. Now we're going to turn to absolute values, which we may have to deal with differently. Okay, so I'm going to change to green here, I think. Before we move into inequalities, let me remind you how we handled equalities that involved an absolute value. So we would work perhaps a more complicated equation down to this simplified form where we had an absolute value on one side and everything else on the other side of the equal sign. And then we knew that the value within the absolute values symbols had to be either a positive value or a negative value. Therefore, we could write a negative x, or whatever is inside the absolute value, equals 2 in this case, or simply whatever that value is inside the absolute values equals 2. And then to solve the one on the left here, we would have to go through the method of solution. So x equals negative 2, or we have x equals 2. So both of those values, negative 2 and 2, have an absolute value of 2. Let's see what would happen if we were trying to solve for a value, the absolute value of which was less than 3. Now remember, the absolute value deals with the distance some number or expression that we can solve for a number is from 0. So let's see, what numbers are a distance of 3 from 0? Well, 1, 2, 3. 3 is, but also 1, 2, 3 in the other direction, or a negative 3. Both of those, if I had these exactly drawn correctly, would have a distance from 0 of 3, or an absolute value of 3. So the absolute value of negative 3 is 3. The absolute value of positive 3 is 3, but that's not really what we're looking for. We are looking for the absolute value of x to be less than 3. So first, let's deal with this algebraically. We know that if we're looking for an x less than 3, if that x is positive, yeah, sure, that works. You could find x's that are less than 3. 2 is less than 3. But we also have to consider what would happen to this inequality if we have the negative x is less than 3. To solve that inequality that I just wrote, we need to divide both sides by negative 1. Okay, and that will give us x greater than negative 3. X is greater than negative 3. Let's look at that. If this is 0, 1, 2, 3. Negative 3, x is greater than negative 3, so I have to use a parenthesis. And we're going to be going that way. How far can we go that way? Well, our other inequality that is a solution here says that it has to be less than positive 3. So our interval here that we could express in interval notation would be negative 3, 3 in parentheses, with the comma between them. But we can take another look at what's going on here with our inequalities, specifically with this inequality. Because usually we write things from the smaller values to the larger values, so let's just flip that inequality. Well, that didn't work. I guess I'll have to do it by hand. If x is greater than negative 3, then negative 3 is less than x. So I can now combine the two. If negative 3 is less than x, and then from here, x is less than negative 3, I can write it in one compound inequality. Negative 3 is less than x, and x is less than 3. Once again, an and statement. The question is, will this always be true of absolute value inequalities? No, you knew it wouldn't. Come on, it couldn't be that easy. Let's look at the absolute value of x that is greater than 5. So I have to consider both cases, a negative x, putting it into the inequality, and a positive x. And now if I divide both sides by a negative 1, on this side I get x is less than negative 5, and then I have my x greater than 5. Let's graph those two on a number line. Okay, and 1, 2, 3, 4, 5. Negative 5 if that's 0, and 1, 2, 3, 4, 5. Positive 5. Okay, I need x less than negative 5. I think I need to extend my number line. All right, I have a less than symbol. It cannot equal negative 5, but it's going to be less than negative 5. Those are the values that will solve the inequality. But wait a minute. Also, from here, values that are greater than 5 will solve this. Now, the tricky part here is that you can't have one number in both areas, can you? So here we have to use a slightly different statement. If we're using the inequalities, we have to say x is less than negative 5 or x is greater than 5. In interval notation, it gets a little more complicated. In interval notation, the left side here, the x less than negative 5, would look like this. Anything from negative infinity almost to negative 5, and then anything from 5 to positive infinity. Well, cannot be 5. Just above 5, just more than 5, to positive infinity. Okay, and between those two, that U in the middle stands for union, meaning that both of those, both intervals, are solutions to this inequality. However, they do not intersect at all. They are separate regions where you can find a solution, and both of them are part of the solution. So the solution is the union of the two of them. So you can contrast those two cases, put them side by side. You see that in the first case we have a compound inequality. So we use this notation and everything can be expressed in one interval or one compound inequality. In our second case, where we're solving for an absolute value greater than a value, we're going to wind up with two separate regions, two separate intervals which is where we get this notation in the name, that we have to combine with either an or, because a number can be over here, or it can be over here. It can't be in both of them. Or we have to put in the union symbol between our intervals. All right, here's our last problem, so let's make it a doozy. All right, the absolute value of 3y minus 2 over 6 is greater than 4. We're going to solve this one for y. Why? Because it's there. All right, to get rid of that 6 over that's on the left-hand side with the y that we need to free from that absolute value, first we're going to multiply both sides by 6 over 1 on that side, which is the same thing as 6 that we're going to use on the other side. So that will give us the absolute value of 3y minus 2. So yes, we eventually have to be solving for the y, but the first thing we have to do is to isolate the absolute value on one side. And now that we've done that, we can deal with the what's inside the absolute value. We have 3y minus 2 inside that absolute value. And if that's positive, then we know it is greater than 24. But also, if everything within that absolute value is negative, it is still greater than 24. So now we just have to solve each of these separate inequalities for y. Let's see, on this side, I don't really have anything outside of the parentheses, so I can just get rid of them. So 3y minus 2 is greater than 24, and then I can just go through the steps of solution, adding 2 to both sides. 3y is greater than 26, and divide both sides by 3. So y is greater than 26 divided by 3. But on the other side of this dotted line, we have a negative that we have to distribute, because that's like a negative 1 there. So negative 1 times 3y is negative 3y. Negative 1 times negative 2 is a positive 2. And that, oh, wait a minute. No, I'm going to do it this way. It's okay. There's another way to do it. You can ask me if you like. Okay, and subtract 2. Negative 3y greater than 22. And now I have to isolate that y by dividing by a negative 3. So that's going to give me y, but I have to flip my inequality. And y is less than, whoops, don't want that negative in two places, negative 22 over 3. And simply to make these easier to put on a number line, I'm going to convert these to a mixed number. And let's see, 3 goes in there 8 times, leaving 2/3. So y has to be greater than 8 2/3. And is an and or an or? Let's see. This would be a negative 7 1/3. There's my number line. My y's are greater than 8 2/3. So 1, 2, 3, 4, 5, 6, 7, 8 2/3. Cannot be equal to that. Has to be greater. So I have to have a parenthesis opening that way. And it stretches to larger numbers, to positive infinity. Or, is this an or an and? It's an or. You can't have numbers that are both less than negative 7 1/3 and greater than 8 2/3. Therefore, we must have two intervals here. We have to have the interval from negative infinity to negative 7 1/3, or negative 22/3, united with, or union, 8 2/3 to positive infinity. Okay, there we have it expressed as inequalities, and that is with an or. We have it down here as interval notation. Negative infinity to negative 7 1/3, united with 8 2/3 to positive infinity. Well, I think that is quite enough of working with inequalities for today. So I will see you in class.